All right, folks, quiz should pretty much have closed out from everybody just about now. So what I'd like to finish up with regard to thermodynamics and thermochemistry, this is going to be our last discussion involving that, and then we move on to something new, is I want to deal with substance heating and cooling curves, because it's a really nice way to kind of pull a bunch of stuff together that we've talked about during this chapter. It's also going to let us address one other thing, and that's the phase change. We haven't really talked explicitly about how to deal with a thermodynamic phase change. In other words, what heat or enthalpy is associated with, say, boiling 1 mole of water to convert it from the liquid state to the vapor state? Or what amount of heat is required to, say, melt 1 mole of ice to get it to 1 mole of water? So we want to talk about those things as well. So heating cooling curve is a great way to do that. So let's sort of see how that's encompassed in this first and only example that we're going to do today. So this example number 1 says that we want to calculate the total heat required to convert a quantity of 5.00 grams of ice, that's the initial state of the water, that's at minus 25 degrees Celsius. So if you think about it, if you have water at minus 25 degrees Celsius, it's ice. And we want to take that all the way to steam at a temperature of 125 degrees Celsius. So you can see what we have to do here in the grand scheme of things. I've got to take my ice from minus 25 degrees Celsius up to 0 degrees Celsius, because that's where we know that first phase change happens. That's the temperature at which ice melts. Okay, then we got to melt the ice. Once we've melted the ice, then what we have to do is to take the water that we have at 0 degrees Celsius, and I got to heat it all the way up to 100 degrees Celsius. Why 100 degrees? Because that's where water gets converted to vapor, right? That's where we boil water under normal temperature and pressure conditions. So then I got to put a little more energy in to get the water to boil or convert to the vapor. And then once I've got the water vapor or the steam, I got to take it up to 125 degrees Celsius. So you can see there's a whole bunch of steps that kind of have to happen here. Now, if you think about it, all of these steps are endothermic, right? In other words, I got to put energy into the ice to heat it up to 0 degrees Celsius. I then got to put heat or energy into that substance to get it to convert from the solid phase to the liquid phase. Then I still got to put heat into it in order to warm it up from 0 degrees up to 100 degrees. Then I got to put more heat into it to convert the liquid to the vapor. And then got to put yet more heat into the system to then get it to steam at 125 degrees C. So all of these processes are going to be endothermic. Now I could talk about this going in the opposite direction as well. And in that case, I'd be taking energy out, and all of those steps would therefore be exothermic. Okay? So let's see how we're going to go about doing this. So we're going to look at it step by step. So our first step here is I need to get the ice to 0 degrees Celsius. All right, so you see that I give you a bunch of information here about the various substances. I give you some specific heat or heat capacity data here. Okay, so those are specific heats of the 3 substances we have to think about: ice, liquid water, and steam. And then I also give you some enthalpies associated with the phase changes. So the delta H of fusion there is the amount of heat I have to put into 1 mole of ice to convert it to 1 mole of liquid water. The delta H of vaporization is the amount of heat required to convert 1 mole of liquid water at 100 degrees Celsius to steam. Okay, so I have to have all that information. All right, so in our first step, we got to heat the ice up so that we can convert it over to liquid water. So that means I got to get it from 0 degrees Celsius, get it from wherever I started, minus 25 degrees Celsius, up to 0 degrees Celsius. So in this case, all I'm doing is I'm heating the ice up. So the equation I want to use there, and I'll call that Q1 since that's my first Q I got to calculate, is just Cm delta T, right? So it's the specific heat of the ice times the mass of the ice that I have times the delta T that the ice undergoes, okay? So all I got to do now is plug my values in. So the specific heat for ice is 2.092. joules per gram degree C. Multiply that by the mass of the ice. I think I told you I had 5 grams of it. Yeah. Now, what's the delta T going to look like here? It's always T final minus T initial, right? Well, my T final here is going to be 0 degrees Celsius. That's what I'm going to heat the ice up to. The T initial is going to be where the ice started, and that's at minus 25 degrees Celsius. So what am I going to get there? I'm going to get a delta T of 25 degrees Celsius. All right, so I had to get heat units back out of this. So let's see, grams will cancel with grams, degrees C with degrees C, and it looks like I'm good. So if I work this out, I think I have room for it over here. I'm going to get, the calculator tells me 0.262 kilojoules. And that's technically only good to 2 sig figs because of the 2 sig figs I have in my temperature. All right, so that's the first amount of heat that I have to put in. And that gets up to 0 degrees Celsius. Everybody okay with that?
I have a question.
Sure.
So you have joules in like the first part of the equation, and then it says kilojoules at the end.
Yeah, let's see. Yes, actually, I made the conversion. It's actually 262 joules. Let me just add that in here. And then I took it to kilojoules. Okay, so then I had to multiply by 1,000, or sorry, divide by 1,000 to get it to kilojoules. Now I could leave it in joules, but I'm going to put it in kilojoules in each case so that I can make my delta H of fusion and delta H of vaporization work with the rest. Yeah, sorry, I just forgot to show you that conversion, but there it is. Thanks. Does that make sense?
Yep.
Okay, good. Thank you. I just left it out. Sorry about that. All right, so the next thing I need to do is I got to convert the ice to liquid water. So there I'm going to use my delta H of fusion, but I got to start with the amount of ice that I've got. So I'll let that be Q2. Again, that's going to be endothermic. I have to put energy into the ice to get it to melt. So that's going to equal to my 5 grams of ice that I start with. All right. Now, I need to convert that to moles. And again, the reason for that is if you look up at my delta H value, it's 6.01 kilojoules per mole of ice that I melt. So that's why I got to get from grams to moles. So we'll say that 1 mole, doesn't matter whether it's ice or water, we'll just call it H2O, is 18.02 grams of H2O. Okay, so grams will cancel with grams there. Now I can use my delta H of fusion. So it looks like it's 6.01 kilojoules per mole of water. Okay, so moles of water cancel with moles of water, and that's going to give me a heat, which is what I need. Now leave it in kilojoules because that's what I'm putting everything in terms of. And I end up getting 1.67 kilojoules. Do my sig figs look good? Yeah, I think my sig figs are good there. All right, so now what have I got? I got 5 grams of liquid water at 0 degrees Celsius. Okay, so I'm not done yet. Next thing I have to do is need to convert liquid water at 0 degrees Celsius to 100 degrees Celsius so I can get to my next phase change. All right, so now what am I doing? I'm just heating water up, right? So I got an equation for that. I know this is Q3, so that's going to be equal to C of the H2O times the mass of the H2O times the delta T of the H2O. Okay? So now if we work this out, Q3, oh, I got to use a different C this time because now I don't have ice anymore. I got liquid water. So I got to use the 4.184 joules per gram degree Celsius. Times the mass. I've still got 5 grams of it. I haven't done anything other than that. So still got 5 grams of the stuff. What's my delta T this time? Going from 0 to 100 degrees Celsius. What do you think my delta T looks like? What's T final minus T initial there?
100.
100, very good.
Wasn't the
Okay.
final temperature 125 degrees Celsius?
Well, it is, but I got to convert it over to steam first. Because remember, we have another phase transition we got to get. Right? Because I want to get steam at 125 degrees. But the first thing I got to
see.
do is I got to convert the water to steam, and I have to get it up to 100 degrees before that happens, right?
Yeah.
Good. I think we got that. Let's see, I'll try to leave it in joules this time, guys. So I get 2,092 joules. And that looks like it's going to be good to 3 sig figs. And now I got to divide by 1,000 to get it to kilojoules. So I go, what, 3 places to the left. So that's 2.09 kilojoules, right? All right. And again, endothermic, I'm putting energy in. So now I've got water at 100 degrees Celsius. So now the phase change. So next thing I got to do is convert H2O at 100 degrees Celsius to steam at the same temperature. And that's an interesting or curious thing about phase changes, is a phase change happens at constant temperature. So in other words, all of the heat I'm putting into the liquid water to convert it to steam at 100 degrees Celsius goes into the phase transition. It doesn't go into actually heating the substance up at all. That's going to happen once I get it all converted to steam. Okay, so I go back to my original 5 grams that I'm dealing with. Still got 5 grams of water. That hasn't changed. We haven't lost any. Okay, so I'm going to convert that to moles. Again, because my delta H is in terms of kilojoules per mole. So that's what, 18.02 grams of water. Okay, so grams will cancel with grams. I got moles of water. Now let's go back and get the right delta H. Now I want the delta H of vaporization, right? Because I want to vaporize the water. So that's going to be 40.65 kilojoules per mole. Okay, so moles of water should cancel with moles of water, and that'll give me kilojoules. All right, so let's see what I got for that. Looks like I ended up with 11.3 kilojoules heat to make that transition happen. And now I've got one more thing I got to do, right? So my 5th step is I've now got water vapor or steam at 100 degrees Celsius, and now I want to take it all the way up to what, 125. I shouldn't say convert, let's just say heat. So I'm not really converting it to anything, I'm just heating it up. Okay, so I'm making hot steam and I'm making it hotter. All right, so now my Q5 is equal to my specific heat of steam times the mass of the steam times the delta T that the steam undergoes. Remember, delta T is T final minus T initial, which in this case is what, 125 degrees Celsius minus 100 degrees Celsius. Okay, so we can calculate what that should be. So my Q for the steam, call that a Q5, is going to be equal to the C for the steam, which I have, that's 1.996 joules per gram degrees Celsius. Times my mass of the steam, still got 5 grams of it, right? It hasn't changed. Times my delta T, which in this case is 125 minus 100, which is 25 degrees Celsius. All right, so grams cancel with grams, degrees C with degrees C. I'll get joules out of this. End up with 249.5 joules. And if I want to convert that to kilojoules, let's see, I'm just going to move the decimal point 3 places to the left. So that's going to be 0.2495 joules. I think that's only good to 2 sig figs, so I'll underline that. All right, so now I've got all the different heat components that I need. So what do you think I'm going to do with them to get the total heat? How do I get a total?
Add them.
Add them up. You got it. All right, so my Q total is going to equal to Q1 plus Q2 plus Q3 plus Q4. And then I had one more, the Q5, right? All right, so let's see what I've got. That's going to equal to my 0.262 kilojoules. How many sig figs did I say I had on that originally? I think it was just 2, wasn't it? So I'll add that up accordingly. All right, plus the next one, the Q2, that turned out to be, let's just double check, 1.67 kilojoules. Plus my Q3, that turned out to be 2.09 kilojoules. And I need my Q4, that was what, 11.3 kilojoules. And I got to add to that my Q5. Oops, sorry, might as well put a number in there. 0.2495. And I'm good to 2 sig figs there. I think the rest of them I had the sig figs worked out. All right, so it looks to me like when I add this up, I'm going to be good to the 10th place ultimately. So when I add them up into the 10th place, it looks like all told, I get 15.572 kilojoules. It looks like I'm limited to the 10th place over there on my Q4. So we're going to call that 15.6 kilojoules of heat. Okay, so that's the total amount of heat I'd have to put into my system, go through all those phase transitions and get the temperature from an initial, which was really cold ice, up to really hot steam. Okay, so that's, you can see why I would call this a heating or cooling curve. You could actually plot this out on a graph and see the whole process if you wanted to. So this is actually how in textbooks you see this mainly expressed. You would see this in terms of temperature, say in degrees Celsius over here, as a function of Q in kilojoules, or the heat I'm putting into the system. Okay, so what you would see is that I start out at whatever my initial temperature was. What was it, minus 25 degrees Celsius. And I'm going to take it all the way up to my final temperature, which was what, 125 degrees. Okay, so what ends up happening is I have to put some heat in to warm the ice up, and then I end up at a constant temperature. So I'm still putting heat in. So notice that my x-axis is still increasing here, but the temperature is not increasing. I'm at a constant temperature because that's where I'm actually converting the ice over into liquid water. And then I have another transition where I end up converting the liquid water up to about 100 degrees Celsius there. And then I have another flat area here, which is where I'm converting my liquid water to steam. And then finally, I have another increase to take me up to 125 degrees Celsius. So you can see the different parts there on the curve. So this first part would be my Q1, the second part would be my Q2, the third part would be my Q3, there's my Q4, and then this last little section here turns out to be my Q5. Okay, so you can actually see this nicely plotted out on a graph. And again, this is how textbooks normally show it. Now, again, this is also a reversible process. So keeping in mind, I could start with steam at 125 degrees C, and I could start taking heat out of it, right? I could start cooling it off. And as I do that, you're just going to take the curve in the opposite direction. And I could go all the way back down to minus 25 degrees Celsius, which puts me back in the territory of solid ice again. Okay, so think about it in terms of the process being reversible in the sense that I can go in either direction. So if I'm going in the direction of heating things up, it's endothermic, right? Because I'm putting heat in. But if I am going in the opposite direction, I'm cooling everything off, then from the point of view of the water, it's an exothermic process. Because I'm taking heat out of the water and converting it to the surroundings, right? So in other words, my water going backwards is losing internal energy or heat. Okay, does that make sense to everybody more or less? Any questions in general about that? Again, it's a very nice sort of summary to this whole chapter, I believe. All good? All right, so I have one of these for you guys to look at in Chem 101. I think it's kind of going in the opposite direction, but similar kind of problem. So let's pop over there real quick. By the way, you guys did well on the quiz. So phase changes, here we go. So let's go ahead and start this. It's about a 10-minute activity here, which is going to be about right. So how much heat in kilojoules would need to be removed to cool 153 grams of water from 25.60 degrees Celsius to minus 10.7 degrees Celsius. And then they also give you some information about it as well. So I think it only has one phase transition in it instead of two, but same idea. Usually if I click there, it'll let me see the problem. Let's see, I want to show the question as opposed to the answer. There it is. Then they gave you some information there. So as you guys work, I just want to remind you that we'll be starting a new chapter. The chapter is going to be on the structure of the atom and interaction of light with matter in spectroscopy. So we're actually moving back around to atomic structure again, which is something we talked about way back at the beginning of the course. But now we're going to focus more on where are the electrons and what are they doing. So that's going to be our topic for Wednesday. So make sure you watch the next video. So we're back to videos again. Yep, looks like we're starting to make a little progress here, guys. And remember, this one's going to be exothermic. So technically speaking, your heat out is going to be negative. But remember, Chem 101 in problems like this has a tendency to like to see absolute values of heat when they talk about quantities of heat added or removed. So remember, you might have to change the sign on that thing. I'll go look at the answer and see if they do couch it. Yeah, they do couch it as a positive heat. So yeah, that's correct. Even though we really know they're taking the heat out. Yep, making good progress there, guys. All right, folks, looks like we're gonna finish up just a few minutes early today. So it looks like, yeah, feedback on this is good. You guys are getting this, so that's good news. All right, I will see you guys on Wednesday. Again, make sure you're looking at the next video and we should be good to go from there. I'll see you on Wednesday.